Alright, so let's get started. This is Unit 7, Universal Gravitation. And this will be a pretty brief PowerPoint, but we'll start off with just Newton's law of universal gravitation. So what this is basically saying is that every particle in the universe attracts every other particle. And this is something that you don't normally, witness, right? It seems like when you drop, something from a certain height, that object falls to the ground. You don't see the Earth, being attracted to that object. But in reality, that is happening. The force of this attractive force is directly proportional to the product of the masses, and it's inversely proportional to the square of the distance between them. So what this is saying is that the force itself, is directly related to the product of the masses. So, if you have two really large masses, the force will be pretty evident. But if you have a really large mass like the Earth and a really small mass like this pencil, the force is substantially less. It's half as much than if you were to have two Earths. Also, it follows this inverse square law. So if you double the distance between two bodies, the force gets cut by a factor of 4. And more precisely, F sub g, so this is the force due to gravity, is equal to some constant, we'll call it g, times m1 times m2 divided by r squared. So you see that the product of the masses is over here, and the square of the distance between them is down here, r squared. And we get that g is equal to this number, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And this is something that you can measure by experimentation, and there's a variety of ways to come up with this constant. Okay, cool. So we say that the gravitational force between two masses is given by this formula. And as an example, let's consider the Earth and a mass. So we have capital M sub E, which will denote as the mass of the Earth. And we'll say that, well, the distance r squared, so r squared is the distance between the two objects, but the distance is the same thing as if you were to measure, if this here is the Earth, and this over here is the object. If you were to measure the distance from the center of mass of the Earth to the to the surface of the Earth, plus some additional distance over here, h. So that's what we would, that's how we're going to represent the distance, because we always know what RE is. It's pretty much constant. We approximate to be constant, and we look at just some altitude above the Earth, and we call that h. So that's what you'll probably see if you look at some of the AP open-ended problems. And now we're going to look at what is the gravitational acceleration of the Earth. So let's think about it. So gravitational acceleration is just, F equals ma. So the acceleration due to gravity is the gravitational acceleration. So if we just write in F equal m times g, so g is going to be our special acceleration that pertains to gravity. And we substitute in F sub g with this expression over here. Then we end up getting g is equal to this over here, and it's also equal to this over here. Now, one thing that you can say is that the gravitational force is not constant, right? Because it depends on this plus h term. But oftentimes we just approximate it to be constant. We say that the object is just going to be slightly above the surface of the Earth, so this quantity down here is approximately just r sub e. We can get rid of the plus h. And that's how we derive the gravitational acceleration for g. We just make that approximation. Any questions so far? All right. All right, so now, for one thing that I always wondered when I was learning this is, so how do we keep objects apart? Like, how do we prevent objects from just all being attracted to each other? Well, it turns out that gravity is a pretty weak force, and it's far weaker than static friction. So this is why, like, you're sitting, you're watching me on the computer right now, and this is why you're not being attracted to the computer, because you have this element of static friction in your chair. Now, for celestial objects, like in celestial objects, we're looking at cases where you're far away from the Earth, and in this case here, you can't really make that approximation because you actually your plus h term here actually matters. It's comparable to r sub e, and in this case over here, the force that causes that prevents attraction between these bodies is centripetal force. And this is why, like, you'll notice that in space you see all these bodies like orbiting each other, and because of these orbits, it creates, like, the centripetal force will balance out the gravitational force. All right, so we're going to move on to Kepler's laws, and first we're just going to kind of state them, and then we'll start looking into how we can apply them. And I don't think you should memorize these. Like, probably the third one's the most important. It's just good to be able to, I guess, recognize them. There's not a lot of, I guess, math involved with the first two. So the first one is that all planets move in elliptical orbits with the sun at one focus. So you have planet, you have one foci here, another one here, and you have an elliptical orbit. It looks something like this over here. And the sun is going to be over here, and you have a planet over here orbiting. The second law is that the radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. And this is pretty cool, and there's a really cool visualization that I can link down below. If you just search on Wikipedia for this too, there's a really cool visualization where you can see this. And the third law is that the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Now that's a mouthful, but just to remember that, like, if this is our ellipse over here, right, we have a semi-major axis over here, and we have a semi-minor axis over here. So we're just saying that this orbital period t, the square of the orbital period, so t squared, is proportional to the cube of this major axis, m cubed over here. Any questions about this? Cool. All right, Kepler's third law. So now we're going to look into the third law a little bit more. And what we want to do is we kind of want to derive a more precise equation that comes up with this relationship. So we want to concoct a formula for the period of a planet orbiting the sun. And what we'll do is we'll first start with Newton's law. So we'll start with F equal to ma, and we know what F is from the previous slides, right? It's just g m1 m2 divided by r squared. That's our gravitational force. So we put that for F, and just remember that the m1 and m2, one of them is the sun's mass and one of them is the planet's mass, and we label it ms, mp, and we set that equal to mp times a. Now here we know that when we have orbiting, we can say that if it's a circular orbit, we can say that it's m times v squared over r. That's our formula for the centripetal force. So we have this expression over here, and now we're going to look at the orbital speed. So the orbital speed is the circumference of the orbit divided by the time it takes to go that far. For instance, the circumference of the Earth's orbit around the sun divided by the time it takes to go that far, the time it takes to go that far is 1 year, and the circumference is, well, whatever the circumference is. So the orbital speed is that distance divided by 1 year. So more generally, we say that this v, our orbital speed, is equal to the circumference, which is 2 pi r, because we're going to pretend it's a circular orbit, and we're going to divide it by t, which is our, how long it takes to go that far. This is just distance is equal to rate times time, that kind of formulation. But here we're doing velocity is equal to distance divided by time. And when we do that, we can substitute it in over here, right? So we can substitute this into this v squared. And we can also, we can cancel out one of the r's over here with this over here. And we end up getting g times, and we can also cancel out this mp's because they both appear over here and over here. And what we end up getting is g times ms divided by r squared is equal to this v squared where we've substituted in divided by r. And if you rearrange the terms, you end up getting t squared is equal to some constant over here times r cubed. And that's exactly what we hypothesized over here. T squared is proportional to m cubed. And, well, I guess here they're using the variable, they're changing the variable for the major axis to r, which makes, I guess, more sense. But yeah, so this is Kepler's third law, and this constant over here is indeed a constant because it's 4 pi squared, and then big G is a constant, and also m sub s is also a constant. It's the mass of the sun. And if you evaluate this, you end up getting this quantity over here. So just in summary, real quick, all we did really was we took, we started with Newton's law. We recognized that we can use the centripetal force formulation, and then we substituted in the fact that we have this concept of orbital speed, and after doing that we can come up with Kepler's third law. So now we'll take a step back from force, and now we're going to look at gravitational potential energy. So gravitational potential energy. So this applies when an object is separated by a distance more than r sub e from the Earth. And if you remember, like sometimes I said that we can just say that an object is on top of the surface, so it's not like it's we can approximate the field, the gravitational field, to be uniform. But sometimes we're really far from the Earth, and in that case we shouldn't make that approximation. We should actually solve for the actual. We should actually solve for the potential. And what we're going to do is, and remember that when we look at potential energy, we have to set a reference point, because potential energy is always it's always the change in energy. There's no such thing as there's no such thing as saying the absolute potential energy at this point is this amount. It's always like a relative kind of thing. It's kind of like an age gap between two people. Like you would look at the difference in ages. You wouldn't look at the absolute ages. So over here, we're going to be taking the reference point of the zero potential to be infinity. And by infinity, I mean an infinite distance away from the Earth. So u sub I is equal to 0 at Ri equal to infinity. And this means that the potential energy, which is given by G mm over R, is going to be negative, right? Because the force is attractive, and it actually requires work to increase the separation of particles. So you would have to put work into the system to get an infinite separation of the two. As R increases, U becomes less negative. So what this means is that as we separate further, you separate the object further and further and further and further away from the Earth, the potential energy becomes less negative and becomes closer and closer to 0, which makes sense, right? Because if an object is infinitely far away, we said that it's 0, and if it's not infinitely far, but it's almost infinitely far, it should be negative, but it should be close to 0, which follows this trend here. It's a little weird having seeing this negative potential energy, but yeah, if this is unclear, do say something in chat, or or comment like on YouTube, and we can clarify, because this is not like a very intuitive concept in my opinion, having this negative gravitational potential energy. All right, so and also just remember that for a system of particles, the total potential energy is just the sum of the pairwise potential energies. And this will be negative, right? Because for each pair of particles, the potential energy is negative, so the sum over all possible pairs is also going to be negative. And the absolute value of the potential energy is the amount of work that's needed to separate all the particles so they're all infinitely far away from each other. And that also makes sense, right? Because if your potential, if you have like 3 particles, say it's like P1, P2, P3, then your total potential energy is going to be U12 plus U13 plus U23, and if you take the magnitude, so these will all be negative quantities, and if you take the magnitude, you end up getting like the magnitude of each one, because they're all negative, and that itself, the magnitude of U12, is the energy you need to supply to move it infinitely far away. So there's that too. And we'll actually see a lot of this in very shortly in E&M. Like we'll see similar concepts of separating charged particles and looking at the pairwise sum to calculate the rest potential. All right, so now we're going to look at the energy for planetary orbit. So consider an object of mass m moving with speed v about a massive object of mass big M. So for instance, we have the Earth orbiting the Sun. So this is a massive object, and we have a small object over here. Maybe I can make it a little bit more clear. So we have a massive object over here, big M, and we have a small object here, and it's whizzing around with some velocity v, or some speed v. Now, assume that the Sun is at rest in an inertial reference frame. So that's a valid assumption. The total energy of the system is going to simply be the sum of the kinetic and the potential energies. Now the Sun is at rest, right? And only the planet is moving. So we have the kinetic energy of the planet, and the potential energy of the system is what? Well, it's just going to be the attraction between the two celestial bodies, right? And we just said that the potential energy is Gmm over R. So big M is the mass of the Sun, little m is the mass of the Earth, and of course it's negative, is from the previous slide. And since there's no non-conservative forces, the energy is going to be conserved at all points in the orbit. Now, there's 2 formulas that we'll give. So one is that if you have uniform circular motion, the total energy is going to be this. So minus Gmm over 2R. And for elliptical orbits, and remember that the semi-major axis is this over here, A. The total energy is going to be the same thing, except we divide by 2 times A, where A is a semi-major axis. Now, there's this idea of escape velocity. So right now we have 2 objects orbiting each other, right? We can talk about the energy. It's going to be conserved. If we have a problem, we just use conservation of energy. Now, there's this idea here of escape velocity. So this is saying, what is the speed needed to reach a certain distance away from the surface of the Earth? So you have an object sitting on Earth, and now the object is going to, by some mechanism, it'll pick up some speed, and what is the speed that's needed for it to go a certain distance? Now, to solve this, we can use conservation of energy, and we say that the kinetic energy is 1/2 m times vi squared, and this comes from the fact that your if you imagine like a rocket, for example, like on Earth, it'll have some initial velocity vi, but there's also this potential energy component because there's the attraction between the two bodies, and the distance between them is the radius of the Earth. So that's where this term is coming from. And this is the initial kind of configuration, the initial energy. And then the final energy is when the object is, at some certain distance away. And there we also have potential energy. And we call the variable R max. So this R max is simply defined to be H plus RE. And the kinetic energy is 0 because we want to supply just enough velocity to reach that point. We don't want to oversupply, or we don't want to have any velocity at that point. And now we just solve for VI, and we end up getting this expression over here. Now, one thing. So escape speed is defined to be the minimum speed needed, the minimum speed the object must have at the Earth's surface to approach infinite separation from the Earth. So this is kind of like saying that, well, we just derived this formula over here, which says that if you want to go this distance above the Earth, you need to travel at this speed. Now, what if I say that I want to go an infinite distance from the Earth? Well, in that case, your h value over here is infinity, right? So your R max is equal to R sub e plus infinity. So your R max itself is also infinity, right? You're infinitely away from the Earth. So if your R max is infinity, this term here is 1 divided by a really, really big number, which is basically 0. So we get rid of this term over here in the infinite case. So we send R max goes to infinity, which means that 1 over R max goes to 0. So we can remove that term. And then when we do that, we can solve. V is just simply then the square root of this expression here. 2g me over r. And this is our escape velocity formula. All we do is if you look at it, like all that we need is the radius of the Earth, the mass of the Earth, and g. So this is something that's kind of inherently tied to a celestial object, and it's dependent upon the radius of the object and also the mass of the object. So it's pretty interesting. Like if you have an object that's that has like twice the mass of the Earth, but it's also has twice the radius, it has the same escape velocity. So it's pretty cool to think about like the various relationships. Okay, so some tips. We got some tips for you. The centripetal force acting on a satellite is provided by the gravitational force between the satellite and the planet. So the velocity of a satellite in circular orbit is inversely proportional to the square root of the radius and independent of the satellite's mass. The second point, the total mechanical energy of a satellite is inversely proportional to the orbital distance and is a negative value and is 1/2 the gravitational potential energy. For non-orbiting cases, you can determine the satellite's physical characteristics through conservation of energy. And in case of, and this is the most important point, is the last one, that in the case of orbiting satellites, the total angular momentum is constant. So the conservation of mechanical energy and conservation of angular momentum, they can both be used in that case here. And then the last point is this term called geosynchronous orbit. And what this is just saying is that if you have a satellite, orbiting Earth, so it's saying that the satellite will orbit the Earth such that the orbital period is exactly 1 Earth day. And that's called a geosynchronous orbit. You can see like geo and synchronous. So yeah, And we're going to look at a problem now, and we're going to use I think in the next part, in part D, we'll have geosynchronous orbits. All right, so the space shuttle, or a space shuttle, is in a circular orbit 350 kilometers above the surface of the Earth, and the mass of the shuttle is given by this value here. So we're being asked, what is the speed of the shuttle? Part A, what is the speed? So, okay, let's think about it. So we're given, if I were to draw a picture here of the Earth, we're given the mass here, and we're given the velocity here. Oop, no, we're not given that. We're trying to find that, but we're given this height over here, h, 350 km. All right, so try it for a second, and then we'll come back, and we'll try it together. And just as a hint, you can use F is equal to mv squared over r. Alrighty, so let's look at the solution. We're going to basically use Newton's law. We'll use this F is equal to mv squared over r because we recognize that there's a circular orbit, so there's centripetal force. Now, the force is given by g, m1, m2 divided by r squared, and recall that one of the masses is the Earth's mass, and the other mass is the shuttle, and the radius is just the radius of the Earth plus the distance the satellite is above the Earth. So it's r sub e plus this 350 kilometers. And we set that equal to m times v squared divided by r. And now we can just solve for so we can just solve for v, and we end up getting 7,700 meters per second. Cool. Now part B is asking, what is the orbital speed of the shuttle? And for orbital speed, we did this earlier in the PowerPoint. We just took the distance of the orbit and we divided by the speed. So the distance is going to be 2 pi times r, right? Because the circular orbit, and we know that the radius of the orbit is just the mass of the Earth, or the radius of the Earth plus the radius of the orbit. If you think about, this here is the Earth here. This radius here is h plus r sub e, right? And then the 2 pi r gets you the total circumference. And we divide it by v, which is what we just found. And plug that in, and we end up getting 5,480 seconds. So that's how long it takes to make, that's the orbital period. Now part C is asking, what is the total energy of the shuttle at that height? And the total energy, which we derived, and remember there are two cases. So one was like the circular case, and the other was the elliptical case, where the elliptical case was just, we use the semi-major axis. But here we have the circular case, so we just use the radius. And we end up getting this quantity over here, where r is just simply r sub e plus the height. And we know both masses, and we just plug and chug, and we end up getting this as our answer. All right, now it gets a little interesting. Part D, what is the new speed of the shuttle when it reaches the space station. And remember, this shuttle now needs to burn the engine so it can go to the space station, which is 250 kilometers above the surface of the Earth. So 250 kilometers we need to go above the surface of the Earth. We're currently at 350 kilometers, and we're being asked what is the new speed of the shuttle when it reaches the space station. Well, we did say that the total energy is going to be conserved, right? So we know now that the potential, so we know the total energy from the previous part, and we know that the potential energy is just dependent on the height. And we know the height is 250, so we can plug that in. So potential energy is known. And the kinetic energy has one unknown, which is just V, and we can solve for V. And we end up getting 7778. So 7778. So it's slightly greater. Now part E, the shuttle then needs to reach a geosynchronous orbit. So how much energy is needed to reach that orbit? And remember, geosynchronous means that the time it takes, to make one orbit is equal to one Earth day, like where it's kind of, it's orbiting in sync with the Earth. And to do this, we'll use Kepler's third law. And over here we have Kepler's third law, so we have t squared divided by r cubed is equal to the constant, right? Because we said t squared is proportional to the constant times r cubed. Let's just rearrange it. And we know what r is. And we know that we can, we know what E is, which is which is like, from the earlier slides. And what we can do is we can find the change in the energy between those two configurations. So I guess just to be a little more clear, like we know what R is because we know what G is, we know what ME is, and we know what T is because T is 1 day. So we can solve for R. And we know what E is because it just depends on R. So this R, by the way, is like, this is the radius that we need to be at. The radius will set the geosynchronous orbit. Like there's a specific height above the Earth you have to be such that your orbiting time is 1 day. So that's what this height is. And this is the energy associated with that orbit. And the energy that's needed to reach that orbit is simply the difference between your current energy and the target energy for the geosynchronous orbit. So taking that difference, we end up getting this as our answer. And that's all for today, folks. Thank you all for coming.